Hello everyone. I am the Hongxiang, a fresh PhD student from a fresh PhD graduate from University of Malaysia. Today, I am going to introduce our novel bioinformatics tool, SIEVE, one-stop differential expression, variability, and skewness analysis using RNA-Seq data. Here is the outline. In medicine, the patterns of gene expression are different between a person who is in a health state and in a disease state. Currently, RNA-Seq is one of the most common technologies for analyzing transcriptome of tissues. And the outcomes of RNA-Seq experiment are often represented as gene counts. The goal of this work is to create useful methods for detecting interesting variation of gene expression between two biological conditions. The typical analysis of RNA-Seq data is a differential expression analysis. The most popular methods are HR, DE-Seq2, and Lima-1. With all assumptions, the gene count follows an elective binomial model. The other model or framework are also used, such as the Poisson-Tweedy, Bayesian shrinkage, non-parent model, and the compositional data analysis framework. Note that LDX2 is originally designed for testing differential abundance for microbiome data. Not all phenol, and we know the DE analysis is very important. Well, not all phenotype-linked genes show DE. Some of those genes show differential variability or differential skewness. More and more researchers begin to recognize that the biological significance of differential variability and differential skewness. A lot of the methods have been proposed, but only 4 DV tests are available and low DS tests. The standard model for DE test are elective binomial model, but the variance and the mean parameters are confounded. The variance is a linear or quadratic function of the mean parameter. And for NB model, no explicit model parameter to summarize the skewness. So based on NB model, it's very difficult to construct the DV and the DS test. So in this study, we escaped from the confinement of the NB model, and we treat the gene as a community and treat it in all genes as a community within our sample and viewed them as compositions. And then we apply the central log ratio transformation. We transform the compositional count data into Euclidean space. And then we can model the transformed data by using continuous model. Let's look at the CLR transformation. The first table is a compositional count table. And then here I give the formula of CLR transformation. Our pseudo value 0.5 is ANDed if the gene expression is 0. And then we transformed the the count data into a Euclidean space. For our method SIEVE, SIEVE models the CLR transform the counts by using the skew normal distribution. Here are the three forms of the skew normal distribution with their properties. And I chose the center parameter form, where the mu is the mean parameter, sigma is the standard deviation, and the gamma is the skewness of the random variable. So here single and explicit parameters can be used to construct the DE, DV, and the DS test. I deleted YGI and the CLR transformed count of gene G in sample I, and assume YGI follow a skew normal distribution with a centered parameter form. And SNR package is used to perform the parameter estimation. After that, all the statistics is used to construct the DE, DV, and the DS test. BY procedure is applied to control the FDR. Here, figure 1 shows that our method SIEVE can identify the 8 classes of genes. For traditional DE method, they only can identify the 2 types of gene. This means that is the non-DE and DE. Here are the 3 objectives of my study. The first one is to check the model fit and then compare SIEVE to the close competitors method for both DE and DV method. 3 real data from GEO are used to do the simulation study. Here are the simulation design. The source code and the SIEVE-R package are available on the GitHub. Let's look at the figure 2. This simulation result is based on simulated Zou dataset. The figure A shows that the skew normal distribution fits the CLR transformed counts well. And figure B shows that for the majority of genes, the fit is good. Figure 3, 4, and 5 give the graphical summary for the DE simulation study. And the red circle indicates my method SIEVE. From those 3 figures, we can conclude our method SIEVE give a better control in both FDR and the probability of type 2 error, especially for the large sample size. The heat maps in figure 6 shows the DE similarity with respect to the mean and the standard deviation of FDR and the probability of type 2 error. We can see SIEVE gives control FDR very well, and overall, SIEVE gives the best performance among 10 DE methods. Figure 7 and figure A give the result of a DV simulation study. And we can say SIEVE control FDR very well with a trade-off in probability of type 2 error. for moderately large sample size. When sample size is 50, GAMLS give a relatively smaller probability of type 2 error. I apply SIEVE to measure RNA-Seq data. For illustration, I choose to compare the Alzheimer's disease to the control group. And the significance score method is used to code DE, DV, and DS genes. This method considers both biological significance and statistical significance. And finally, the functional enrichment analysis is conducted. The Volcano plots are given in figure 9. The red line indicates the disease boundary. The genes located at the top left and the top right corner are flanked as DE, DV, and DS genes. The bar diagrams given in figure 10 and 11 shows that SIEVE can recover most of DE and DV genes of interest. Figure 12 gives the distribution of the 8 classes of genes returned by SIEVE. As expected, the majority of those genes are non-DE, non-DV, and non-DS. For the remaining, about 50% of genes can be detected by traditional DE test. For the remaining 15%, pure DV, pure DS, and the DVS genes can be not identified by traditional DE test. This result tell us that if we only consider DE test, we may miss the opportunity to discover the alternative patterns of the distribution variations. Table 3 presents the concise groupings of 18 geoterms obtained using all 5 gene lists into seven biological aspects. This result shows incorporating the DV and the DS enables a more comprehensive understanding important biological processes involved in Alzheimer's disease. The last 3 columns are the DV and the DS gene lists. Okay, here I list some examples of enriched biological processes which can be reported to be associated with Alzheimer's disease. About the future work, for SIEVE, the first one is apply the empirical Bayesian shrinkage approach to improve the estimation of the parameters, which may lead to better detection of DE, DV, and DS genes. And the second one is apply Karp-Bank-Leibler divergence of the skewness model to construct the differential distribution test. Okay, in summary, SIEVE is the first method that performs the DE, DV, and DS test simultaneously for RNA-Seq data. It is the first method for DS test. The simulation study shows that SIEVE gives the comparable or superior FDR and the probability of type 2 error. The real data application shows that SIEVE enhances the types of functional enrichment and analysis by providing DV and DSG and the candidate genes. Okay. Here the right side is my supervisor, Dr. Kang, and in the middle is he is Dr. Hiroshi from Kyoto University. He gave me a lot of suggestions for plotting the figures. Okay, here is the list of the publications. Thank you.
Thank you for interesting talk. I have a question about your method. You said that you treated the genes as a community.
Yeah,
and compare the distributions, assuming the skewed normal distribution, right?
Yeah.
So I think you are dealing with, how are you dealing with the many samples? I mean, the replicates. Basically, your method is applied to just one replicate.
Here I use the biological replicate. I did not use the technical replicate.
You didn't?
I only did the biological replicate.
Yeah. I'm interested how to use the biological replicate, how to integrate the biological replicates into a model.
Sorry?
How to integrate your biological replicates into your model. I mean, there are so many, for example, patients, you know.
Yeah.
How to integrate, yeah.
How to integrate?
Okay, I will ask you later, sorry.
Okay, sorry.
Another question is about the simultaneous analysis of DE and DS, you know, and then your detection level decreased, right? So why your detection level was deteriorated in the simultaneous?
Because recent years, more and more researchers recognize the biological significance of the variability and the skewness. This is one reason, and for another reason is for discrete model. It's very difficult to analyze the differential variability and the differential skewness. So I modeled the data under another data framework and tried to use the continuous model. Yeah.
Thank you.